We've been drawing a single chair form of cyclohexane, but in reality, it isn't stuck in a single chair conformation. It can interconvert via what's known as a ring flip. So let's start by drawing the conformation of cyclohexane that we've been working with. It looks something like this. And then let's go ahead and identify our up carbons and down carbons. So I'm going to put a blue dot on the up carbons and a red dot on the down carbons. I'm also just going to give every carbon in the ring a number to help us keep track of them. So I'm going to start at the bottom left and number clockwise. Now we have our ring so we can keep track of what's going on. So in the process of this ring flip, basically what happens is one side of the ring will flip up, the other side will flip down. So let's start, and we're going to start here at carbon 1, and this down carbon, I'm going to flip it up in this direction. So when this happens, the only thing we're really moving is this carbon 1 up. This portion of the ring should pretty much stay the same. So I'm going to draw it basically as is. So we have carbons 2 through 6. And let me just go ahead and highlight these so we can keep track of them. And then really what I need to do is just draw carbon 1, which was a down carbon. It now ends up upward, like this. So this gives us an intermediate conformation, which is known as the boat conformation. So we go from a chair to a boat. And then at this boat conformation, on the other side, so we flipped 1 up first, now 4 is going to flip down. So this up carbon flips downward. And when we do that, we end up with the other chair conformation. And as we draw this, basically if you notice how in the first chair these bonds were slanted to the right, in the other chair conformation they're going to slant in the other direction, they'll slant to the left. Kind of like that. And then we just connect them as we've been doing. So now we have our other chair conformation. And let me go ahead and highlight the carbons once again. When we did this flip, 1, 2, and 6 really didn't change much because we flipped the other side of the ring. So there's 1, 2, and 6. But then carbon 4, the blue carbon, flipped down. And then 3 and 5, kind of once 4 flipped down below those, they ended up. And now we have the other chair conformation. This is another good opportunity to get out your model set and build cyclohexane. So let me show you what you're going to do with this. So we have our 6-membered ring, and if you look at this from the side, hopefully you can see the chair conformation. You can see that we have the bottom of the chair, carbon 1 is here, top of the chair, carbon 4 is right here. So if we follow what we did in this ring flip, the first thing I do is flip carbon 1 up. When we do that, that gives us this boat type conformation. Then this carbon, which is number 4, flips down. When we do that, now we end up with the other chair conformation. So now, just a couple of key points about the chair conformation. During the cyclohexane ring flip, Up carbons become down carbons, and down carbons become up carbons. The second thing has to do with the relative energy of these conformations. So in fact, between the chairs and the boat is about 7 kilocalories per mole higher in energy than the chairs. And for that reason, the molecules really don't want to exist in the boat form. So at any given time, 99% of the molecules are going to exist in one of the chair forms. The other thing that we have to look at is how a ring flip affects the substituents. During the ring flip, your axial substituents will become equatorial substituents, and your equatorial substituents become axial substituents. Let's draw a chair, do the ring flip, and see what happens to the substituents. So here we have a generic chair. I just drew 3 substituents on it for us to look at. I'm going to number this. This isn't IUPAC numbering. This is just a bookkeeping tool for when we go from one chair to another. So I'm going to start here at the bottom left and just number clockwise. And then let's go ahead and label each of these substituents. So X is axial, and it's pointed up. And if you ever struggle to see if it's pointed up or down, all you need to do is just draw a line on the plane of the carbon of the ring and look, is it above the line or below the line? Here it's above the line. Next, substituent Y is equatorial, and it's pointed downward. Again, draw a line at the carbon, see if it's pointed above the line or below the line. It's below, so it's down. And then finally, substituent Z is equatorial, and it's up. All right, so let's do the ring flip. This is equilibrium, so I'm using equilibrium arrows because there's interconversion back and forth. And now when you draw the other chair, you can't just redraw this chair. You have to draw the chair where these side bonds are slanted to the left instead of the right. So again, you can start it the same way, just kind of draw like a propane, then draw in your side bonds, and then we can connect those up, and then you have your other chair. So set your reference point. I like to just set carbon 1 as my reference point. There's carbon 1. When we do the ring flip, it flips up, 4 flips down. So this is carbon 1 on the other chair. Set that as your reference point, number that as 1, and then just number the ring clockwise like we did in the first chair. That way you keep track of all of your carbons. All right, I'll just start with carbon 4, and if it helps, you can draw in the hydrogen. So every carbon has 1 axial and 1 equatorial substituent. The axial shown, so the equatorial must be just an implied hydrogen. And in the other chair, carbon 4 will still have an axial and an equatorial. 4 is a down carbon, so the axial points straight down. The equatorial points up and to the side. So we need to figure out which one is which. Well, the X was axial in the first chair. After the ring flip, axials become equatorials. So X is now the equatorial bond. And then the hydrogen goes from equatorial to axial. So now X is equatorial. But a really, really, really important thing to keep in mind when you do the ring flip, it still needs to be pointed in the same direction. It's still pointed upward. It doesn't switch from up to down. So again, here's kind of your reference plane. It was up. Here's your reference plane. It's still up. Always check that. Make sure it starts up, stays up, or starts down and stays down. The only thing that changes is axial to equatorial, equatorial to axial. Okay, Y is at carbon 2. So let's move to carbon 2 in this ring. It was equatorial. In the ring flip, it's going to be axial. Carbon 2 is a down carbon. The axial will be straight down. Draw that straight down and put the Y in place. You can draw the equatorial hydrogen in, but you don't have to. So Y is now axial, but it's still down. Again, that's very important. Down, still down. And then finally on carbon 1, we have the Z group. It was equatorial. It becomes axial. So carbon 1 is an up carbon on our second chair. So the axial is straight up. So draw that in. And we put in Z. So it goes from equatorial, it's now axial. And it's still up. Let's try to visualize this now with our molecular model. So here is atom X, which is axial and up. Here is Z, which is equatorial and up. And then it's sort of hard to see here in the back, but that is Y, which is equatorial and down. Then during the ring flip, we flip carbon 1 up, carbon 4 down. When you do that, now if you look at this chair, now we can see how, let me skew it around so you can see it, X is now equatorial, Z is now axial, Y is now axial. So again, this would definitely help for you to build your own model and do this ring flip. And then just to help you visualize it, here's a picture of each model, and you can see the comparison of the drawing to the actual molecular models.